I just finished my, so to give you a bit of context, I just finished my DPhil or PhD, so in Oxford, and I was working on MgB2, and I'm a materials engineer. So I've really looked at it as a materials that I try to optimize, and I've looked at it, I transformed it, and then I tried to understand how all the processing parameters I could play with had an influence on the microstructure of MgB2, and eventually also how it influenced the properties, in particular the superconducting properties of MgB2. So why MgB2? Well, MgB2 is in fact a great research superconductor. And when I say research, it's because firstly, we can make it with precursors. Our pre-synthesized MgB2 is also widely available. So it's easy to get our hands on it and then play with it. MgB2 can be manufactured using a broad range of techniques. Even if I only saw it with conventional sintering and also more advanced sintering, you have also wet method and also a lot of other different methods like deposition or thin films. So you can really process it with a wide array of techniques. But the most important thing, I think, for research in MgB2 is the fact that it's very resilient. And by that, I mean, it takes a lot to kill its superconductivity. And this is in sheer contrast with the talk we've seen just before. In HTS, we can see that if you have a little bit of misalignment, it doesn't really like it. In MgB2, actually, you can do a lot with it. So you can add grain boundaries. You can actually have a lot of grain boundaries. MgB2 quite like it. You can add a ton of stuff. So doping with carbon, any kind of oxide, nitride additions, and it still superconducts. And obviously, you can also do a lot of thermomechanical treatments. So for that, it's a really interesting materials because you can generate a wide variety of microstructures, and then you can investigate how these might be beneficial for the properties. But on top of being a good research superconductor, it's also a promising engineering superconductor. Why? Because it's cheap. It's cheaper than most of the fancy and more exotic superconductors like the HTS. It can be used in polycrystalline form. And in fact, on the right, you can see a graph which shows that the JC can be correlated. So the improvement in JC can be correlated to the grain size. And if you have smaller grains, you have more pinning centers. And so JC is improved. So for this, it's very interesting. And again, it shows that MgB2 is resilient and it's easy to process. It can be also processed by scalable techniques so that for later stage in commercialization, you can go from the lab to production, not without too much hassle. And then it has a relatively high TC of 39 Kelvin. So that's an advantage compared to conventional LTS, such as niobium titanium or niobium tin. So why do we work on MgB2? Well, in my case, we want to make bulk superconducting magnets. And the two important applications here are small compact MRI machines. At the moment, are entering the market with permanent magnets. Although this is problematic because permanent magnets, as in ferromagnets, have limitation in terms of field capability. So you can't really go past 1.5 Tesla. And this limit, which is interesting to ferromagnetism, we can overcome it because the way the field is generated in superconducting magnets is very different. And so we don't have that limit. And we can go, in fact, to much higher field. And we have achieved quite recently almost 3 Tesla in a conventional MgB2 bulk, in fact. It's also interesting for magnetic drug targeting. In these applications, you need a compact magnet to go quite close to the body, but also you want to generate a very big field. And so these are the two applications where bulk superconducting MgB2 could be used. So What I've done first, so surprisingly, after 20 years of research on MgB2, I thought that some parameters were explored, in particular the sintering pressure, or like the sintering time, the rate at which you heat up your powder. But one of the most important parameters, so the sintering temperature, which is well known to have the biggest effect by ceramics engineers, it wasn't too clear what it was doing to MgB2. So we started simple and had some MgB2 powder pre-synthesized and then sintered it at different temperatures from 900 to 1200 degrees C. And we obtained those little pellets, which is slightly bigger than a 1 pound coin, 20 millimeter in diameter. And then with those bulks, we could do our characterization. So the first thing we realized when we sintered is that it had a big effect on the microstructure. So we can see as we increase the temperature, we go from a kind of loose stack of powder, which is barely sintered, to, for 1200 degrees, a solid material, which has very little porosity. And by increasing the temperature, we had a huge effect on density. So which increased from 68% for the 900 sample to almost 96% for the 1200. So that was an advantage of the sintering temperature. But obviously, material scientists know that usually high temperature can also have negative effect. In particular, we saw that MgB4, which is an impurity, increased from 11 to 16.8%. And that's an impurity, unfortunately, we don't want. And also, we had some coarsening, so the MgB2 grains became bigger. How did that influence the properties? Well, here's the critical current density of those 4 samples. And the main thing is that we saw a very large increase, so a 6-fold increase in JC, and in particular in JC at low field. But you can see for the purple curve that this improvement is pretty much on the whole field range. And then we had no effect on the irreversibility field. So it was actually quite a positive result, because it seemed that even though we had a bit more MgB4 and we had some coarsening, here what played in favor was just the huge increase in density. And so the next step obviously was to understand why that would be the case. And it's quite actually counterintuitive that you have a better JC when in fact you have coarsening. And this can be explained quite simply, because in fact what we measure is not the intrinsic JC, but rather a macroscopic JC, which depends heavily on how connected your microstructure is. So in the low temperature sample, we can see on that schematic microstructure that we had small current loops restricted to individual particles because the connectivity was quite poor. And then on the right, for higher temperature, and that's also to put in perspective with what we've seen in the SEM images, we have a much more connected microstructure. So there we have macro current loops. And because we extract JC from microscopic magnetization measurement, it appears that obviously the JC is higher. Does this matter? Well, yes and no. Yes, because we actually would like also to know what's the intrinsic JC, but no, because in our case, the application is to make a magnet, a bulk magnet that traps as much phase as possible. So what we care about is just the macroscopic performance. So in fact, what's relevant in our application is the macroscopic JC, not so much the intrinsic one. And this was like just to start with the basics. And when we understood a bit like how those simple parameters worked with pure MgB2, we could add a level of complexity to the system. And here I'm going to introduce a concept, which is the oxide dispersion strengthen concept. So in alloys like steel and superalloys, metallurgists have done for 40 years something which is very simply taking a metal and putting tiny oxides in it, oxides that can be as fine as 5 to 10 nanometers. And so the idea behind this was, can we take this concept that seems to work so well for materials that have strong mechanical properties, but instead of pinning dislocations or grain boundaries, which improve the mechanical properties in steel and superalloys, can we take these little particles and put them in a superconductor, here MgB2, and will they pin the vortices? And so by having extra pinning centers, can we improve the superconducting properties? So that was the main questions behind my thesis. And to do that, we had to design a process, obviously, so which was inspired from what is done with superalloys and steel. So we had commercial MgB2 powder and then yttrium powder additions. So between 0.5 and 10.8%. We put them in a jar with some steel balls, and we did some high energy ball milling, so to mix everything together. And then with these composite powders, we use the field assisted sintering technology. So this is sintering, slightly more advanced than conventional sintering. So essentially we have a graphite die and 2 graphite punches. We put the powder in between, and then we have a lot of current going through the punches, and that goes through the material. And with Joule heating, you heat up very quickly your material, and you also apply pressure. And so that cooks your material and sinters it. The first step was obviously to manufacture the powder then. What we did is that we ball mill for different amount of times, and we realized, so these are some transmission electron microscope image, that if you ball mill only for a short time, so the big gray particle is the MgB2 matrix, and then the smaller white ones, or that also are green and blue on the yttrium and oxygen maps, represent the yttria particles. And after a very short time, we can still very much see them. They are discrete and embedded or on the surface of the MgB2 powder particles. And as we increase the milling time, they slowly dissolve in the particles. And that is also observed in steel and superalloys, where we see the yttrium oxide dissolving in the matrix. Again, if we take some XRD results to confirm that, we saw that after 6 and 12 hours of milling, the yttria peak completely disappeared, which also confirmed that probably the particles dissolve in the matrix. So that's a really good result, because it's always the first step of an ODS process, is to first dissolve it in the matrix, and then you want to make it precipitate in a controlled fashion, so that to have the good properties of that small dispersion. So the second step was obviously to try to see if we could reprecipitate and have this microstructure. So we had a few powders. So one that had 0.5% of yttria, ball milled an hour, one with the same quantity but ball milled for 12 hours, and one which had slightly more yttria. Again, we put it in the nice fast machine, and then we have that pellet that we can analyze. We had this type of microstructure. So this is again some transmission electron microscope. And we were surprised that in fact we could actually reprecipitate yttria just in a slightly different form, so in YB4. And that's not a surprise, since there's a lot of boron in MgB2 and YB4 is extremely stable. So what we did is that we started with yttria, we dissolved it, and we had yttrium and oxygen probably dissolved in the matrix. And then in situ, we reprecipitated YB4 and MgO. And as you can see, they are fairly small. So we didn't quite hit the 5 to 10 nanometers range, but we were between 15 and 50 nanometers, which is quite promising. And what it did on the properties, well, not so much on TC, which is good because we don't want to drop TC too much. So here we lost 1 or 2 Kelvin, which is quite minor. But the positive thing is that by having actually 0.5 or 2% yttria And by ball milling for long enough, so that means 12 hours, we can see that we shifted the curve, we pushed it upward and outward, which is exactly what we wanted to do, because then it meant JC performance was improved with the new pinning centers. What was interesting is that if we only ball mill an hour, we didn't have any improvement. And that can be correlated to the microstructure, which essentially showed that for low milling time, we didn't have a small dispersion, but rather big agglomerates, which meant that actually we didn't mix it well enough and for long enough to have the positive effect of the new pinning sites. Now, another interesting thing was to play with the temperature. So here, we saw that temperature again had a huge effect because after ball milling, the material is heavily damaged. And you can imagine having a lot of dislocation, grain boundaries, and the crystallinity was damaged. And so if you only process it at low temperature, you still have a high concentration of defects, which hinder superconductivity. So your TC is lowered and can be lowered by actually almost like 10 Kelvin. And then slowly, as you processed higher in temperature, you would recover that TC. And that's just because you annihilated those defects. But what was interesting was this part, the effect on JC. We saw that in simple MgB2, increasing the sintering temperature had only a positive effect that we can find here at low field as shown by the green arrow. So if we increase the processing temperature, we have better connectivity, better macroscopic current loops, and so we increase the JC at low field. However, in here, because we don't have just MgB2 anymore, we have those small precipitates, the effect of coarsening is seen much more. And basically we can see with the red arrow that as we increase the temperature, we increase coarsening and we reduce dramatically the high field improvement that we had by putting those new pinning centers. And you can see that actually the curve kind of rotate around a point there. And it shows that there is clearly a compromise between better connectivity and coarsening. So that's obviously quite annoying, but we went a bit further and we tried to overcome this compromise. And one way you can do that is just like go back to the textbook and just see if I can't increase the temperature, what else could enhance my sintering? Well, pressure. Pressure is really good to enhance sintering and so you don't have to go as high in temperature. So we had access to very nice cubic press that are usually used to make diamonds. And so here in purple, we can see that by processing at the lowest temperature of the graph, so 900 degrees, not only we improve the properties at low field, but also we improve hugely the properties at high field. So we did overcome what we thought was impossible and what was that compromise between improving connectivity that requires high temperature and also decreasing sintering, which actually prohibit the use of high temperature. So using a new sintering process is actually quite interesting to overcome limitation of simpler process which only use a low amount of pressure. So the conclusion of this talk is when we play with materials engineering and try to have new microstructures in materials, it's first important to understand the basics and then to build up in complexity. So we saw that in MgB2, sintering temperature has only a positive effect on JC performance and improved JC over most of the field range. When designing complex microstructure, the story is a bit different. We managed to actually show that the ODS concept can be extended to superconductors. And with TM and XRD studies, we also showed that yttria actually dissolves nicely in MgB2 and then can be smartly reprecipitated into very small form. And that in this case, because now we had like another component in the system, so those little particles that act as extra pinning center, the centric temperature has a strong effect on the JCB curve, but not only positive, because with the coarsening now, higher temperature also reduce high field properties. However, with smart processing techniques such as ultra high pressure sintering, this can be overcome, and then that leads to like new ways to process high performance MgB2 bulks. That's it for my talk. So I would like to thank everyone that has worked on this project for the last 3 years, and thank you very much.